Welcome to the discussion on one of the most important topics in corrosion of metals and alloys. The topic of discussion is stress corrosion cracking. So far we had looked at the corrosion of metals from a perspective where there are no applied stresses acting on the metal. We discussed the galvanic corrosion where you had dissimilar metals coming in contact with each other electrically, and we said that the anodic member of the couple will undergo the corrosion aided by the cathodic member. We then went on to discuss the crevice corrosion in the structure. When you form a crevice because of the fabrication issues, the crevices act as sites of corrosion. We looked at the passive metals, and we said that the passive film can break down under certain conditions, maybe a mechanical damage, or it could be due to the specific ions present in the environment leading to pitting corrosion. Then we looked at what happens when there are the transformation in the material, especially in stainless steels, that leads to sensorization. We looked at the intergranular corrosion of the stainless steel and this relevance to welding and fabrication. The intergranular corrosion again not only confined to stainless steels, it can happen in any other material, more so in magnesium alloys and aluminum alloys and copper based alloys when the grain boundaries are becoming electrochemically active. In all these cases we also assumed that there is one more case we also discussed where we call as selective leaching and de-alloying. In all these cases we assumed that the environment is static in relation to the material, and we looked at what happens if the environment moves in relation to the structure, to the material. Then we had looked at 3 different forms of corrosion and flow assisted corrosion: erosion, corrosion damage, the cavitation damage we talked about, where the environment we considered was a fluid. It could be a gas, it could be a liquid, and of course in all these cases you can have a suspension of the solids, but essentially it is a fluid. We looked at one more case where the contact surfaces are in motion. Okay. In the contact surfaces in this case are a solid state, right? They are solids. One metal against another metal and one metal against another ceramic, for example. When they are relatively moving and when they are under load conditions, what kind of corrosion occurs? We call them as fretting damage. The loading conditions that are acting on these contact surfaces only they are not considered in terms of what happens in the bulk. The load, the stresses that happens in the bulk were not considered. In fact, these contact surfaces, the interface, the loading is the predominant factor. But most often the engineering metals and alloys are made for structural applications. They bear the load, right, be it a ship, a pipeline, or a reactor, could be a pressure vessel for example, or could be aircraft, or you can name quite a few actually. In all these cases, the metallic structures are experiencing certain amount of stresses. You can also start classifying stresses into different categories. It could be a tensile stress, it could be a fatigue stress, or it could be a shearly retorsion test, stress can happen. So, when you have this, when you also have an environment acting on the surface, the failure mechanisms are different and they have very serious consequences. In fact, you would see that the metal hardly corrodes in terms of visible changes, loss in weight is hardly seen at all, but it can lead to cracking, it can lead, as a result of which it can be leaking and and structural instability, and there could be safety issues involved. So, what we are going to look at in this particular, maybe today and in a couple of days, is how a metal under tensile loading condition and also exposed to the environment respond to it. Okay. What is the mechanism of such corrosion process, and what are the factors that affect such kind of corrosion, and how do you prevent them, and if there are any kind of fingerprints, characteristics of that form of corrosion is also important. So, these aspects we are going to see. So, before I go into it, I just want to show certain illustration how the corrosion can really affect in practice. This in fact is an ongoing work which we are doing now. This is the reactor, in fact it is a pressure vessel, I would say, it is high pressure. It is meant to produce an aromatic compound, most of you know the aromatic compounds are, as a special characteristics, and they are synthesized using inputs which are mostly organic, and maybe sometime you may add sodium hydroxide, you may add water. They are subjected to high temperature, high pressure conditions. The reactor that you are seeing here, do not worry about all these inlets, outlets, all these stuffs actually, okay, because there are, you see, they feed hydrogen, when you feed hydrogen, then there are a lot of precautions that you have to take, you can't simply do it. So, there are so many ports. It was made up of 304L stainless steel. The company wanted to increase the production, they went from a smaller reactor to a bigger reactor. In just 4 months of its inception, commissioning, okay, the reactor start leaking. And I do not think, when you have hydrogen, you really would like to take risk of that actually. And if I look at it, look at the inner walls of the reactor. Normally we do NDT, right? NDT is one very versatile NDT is dye penetrant test. Some of you are aware of it, right? You apply a dye on the surface and you wipe them out, and you can just you also add another elutant to the surface, and so the die comes to the surface, and wherever the crack, the die penetrates and comes back to this. So you will be able to see this, the subsurface cracks, even surface cracks, using the die penetrant test. When you take a cross section of that, you see how the cross section looks like. I hope you will be able to see very fine cracks starting from the surface and moving towards this. It is a very thick vessel of 50 millimeter thickness. It is a 304L stainless steel, and you find that it just failed in 4 months. If you look at little bit more in detail at higher magnification, okay, and you will find the cracks are microscopic in nature, and the microscopic cracks turned into a macroscopic failure, okay, and you guys now are reasonably familiar with metallurgy. You see that these cracks are all branching now, and you see some of them are called transgranular cracks, okay. We will come back to this soon. So 4 months time and the reactor started failing. This is a heat exchanger, okay, this is a kind of schematic of that, okay, and it is called as air condenser, right. You want to dry the air, so you need to, especially when, see what happens, in industry every heat is important, right. You create heat, you just do not want to let it out, right. You take the heat out from that. Heat is essentially energy, right. So the air comes out of the reaction process, you need to remove the heat because it costs money, and this is the condenser, right, air condenser, right. It takes the heat and it is called as a cooling water system, okay. So what you do here is that you can see here that there is an inlet here, okay, it goes inside this outlet here, and it is a horizontal heat exchanger, and it is made up of 304L stainless steel. The air inlet, the temperature is about 150 to 160 degrees Celsius at a pressure of 10 kg, centimeter square, and you have a cooling water, enters here and comes out, air enters here and then it comes out here, okay. It is a counter current process, right, it is what happens. The material used was 304L stainless steel, it is a fertilizer company, and the cooler in operation was for 6 to 7 years, not longer. And the tubes which are inside, 63 of them started leaking at all actually. That was a problem. So they are all premature failure, right. You just take these tubes and see the tubes in a microscope. This is the cross section of the tube. You see here the crack started from the external thing where the water went through. The water went through this, okay. So from wherever the because the surface is is covered with water, and you start cracking. This is called cooling water. This is not a distilled water. It is of course a pure water, not like your DM water. Again, you see a kind of branching of cracks. This is one of the characteristics of stress corrosion cracking. And if you know, if you do a tensile testing, or if you have the mechanical loading is a failure, you only see one crack. The cracks are not branching at all. The crack morphologies we will discuss shortly. And this is also some kind of transgranular cracks taking place. Look at this in a scanning electron microscope in detail. See the surface is quite brittle surface, right. is a brittle surface, it's a brittle surface. And those guys who are with the metallurgy background, you will appreciate, you will able to understand what brittle fracture is. And those who are not from the metallurgy background, I want to show how a normal fracture should look like in scanning under a microscope. Okay, you see this here. This is a material failed in air in the absence of environment. It is a tensile failure, and hope you can see this. It is called a fibrous failure. It is called a dimple failure and dimple fracture. And you can see the fibers. You know, the metal has nicely elongated. They just flew, nicely flew, right. So this is a kind of ductile fracture. You see, when you have simply failure in air. I suppose that it looks like a glass that failed here. Okay, so the problem in stress corrosion cracking is that it can cause a premature failure, and it can lead to certainly, see, it is not going to cause too much of corrosion. See here now the surface. Okay, this is the surface internally, and you do not really see much of corrosion at all. I hope you were able to see this clearly. Now it is almost, but then wherever there is a crack happen, and subsequent place you are not seeing any corrosion. So visually they are not undergoing severe uniform corrosion at all, and so this corrosion is very localized and is called as a stress corrosion cracking. Now stress corrosion cracking has been really a problematic thing actually. It's a problematic thing, and in fact if you look at the historical perspective of that, I am not going to discuss. There is a paper by Sergei Siplov, I think give a reference later, and he has given very nicely the history of stress corrosion cracking. Actually in the year 1873 at Manchester, a guy called Williams H. Johnson. He did a very interesting, curious experimentation. What he did was he took steel, okay, and then he dipped in hydrochloric acid, okay, and also in sulfuric acid, both the acids. He did a nice, just dipped it, and then he carried out a tensile test. He found ductility reduced significantly. In the year 1874, another interesting person, and Osborne, Reynolds. He did another interesting experiment. He found that ductility loss can be reversible. you expose it to the environment and do tensile testing, and you see there is a loss in ductility, but you just leave it for quite some time in air. He says that you do a test after a few months, and major part of the ductility loss can be recovered actually. That was a very interesting experiment that was done. Now subsequently, and in the year 1886, the guy called Roberts Austin, what he did was he took 22 karat gold and drawn into a wire, right? And then he exposed to ferric chloride. Wire got cracked. Probably this is the first such observation which talks about the so called stress corrosion cracking. The earlier observations, they pertain to hydrogen damage, hydrogen embrittlement, we will talk about later. So they were all academic experiments, they are more academic, and the importance of such kind of loss in mechanical properties. You see what is here, there is a loss in ductility taking place. They have not realized, they started realizing it in the early 20th century. There was a time where there was industrial revolution taking place, right? Lot of technologies were developed actually, and it so happened the invention of steam driven locomotives, right? The steam driven locomotives first saw the problem of stress corrosion cracking, how severe it can be, right? Now it is simple water and you generate a steam, and that is used to drive the locomotives. Now is used, same steam is used now to generate electric power, right? Now people have used electric powers. Now this is a problem because you see here, this is very mind boggling. 1865 to 1870, 288 boilers in UK, and in 1867 to 1868 we had 441 boilers in USA exploded. It was really kind of and you see the consequence of explosion, right? The pressure vessel actually, and the steam at that temperature, pressure, lot of casualties actually. How it happened? The steam locomotives made up of steel, I mean not locomotives, I am sorry, the boilers made up of steel, and they are fabricated using what? How they fabricated? using rivets, right. What is then you put a sheet and then you put a rivet and then you just what you cold compress it, right. There will be more stresses, there will be lots of residual stresses in the system. And when you use water for the boilers, the pH is increased, otherwise what happens, the steel will corrode, right. The pH used to be around about 10 or so, and then what happens when you boil the water, you take the steam out, what will happen to whatever remains in the boiler? How do you make the pH of the water higher? You add sodium hydroxide, right, and you increase the pH to let us say 10, and you boil and evaporate. So what happens now? With the time, the sodium hydroxide concentration increases and then it leads to cracking. So thus the name emerged, we call as caustic embeddlement. The caustic embeddlement, now we all know that it is a simple mechanism of stress corrosion cracking, right. But those days they called it caustic embeddlement because wherever the caustic accumulated, see what happens when you have a sheet and then you join them like that, right, join them like this, and you put a rivet here, okay, and this gap there will be accumulation of the sodium hydroxide and start giving rise to crack. Historically, there are one more incident that also brought the attention of people. Season cracking of brass cartridges. It's a bullet, right, and you mount a bullet. Right, you crimp here, right. Okay, this is a hard one, maybe a steel or something like that. Okay, this is made up of brass. So they, what happened was the cartridges started cracking during the winter time. See, they was traced to India first actually, because the British found that these cartridges fail during winter and monsoon time. Winter and monsoon time, where what happens to organics? Suppose you have organics, they decompose and then they generate ammonia. The ammonia causes cracking of brasses. So these are the names given to stress corrosion cracking because they are associated with certain events, okay, and they are all in fact can come under stress corrosion cracking of metals. Why is that you should worry about stress corrosion cracking? Why bother about stress corrosion cracking? We have, I think, some mechanical engineers, right, background, right, I think. I give a material and I ask you to use that material to design some structures, maybe a pipeline or maybe a foot over bridge, whatever, okay. So, what input parameters do you take to design the structures? Of the material, right? Of course, it has to take certain load, okay. So, the loads are given to you, okay. So, what input parameters of the materials you would consider? Yeah, yield stress, yield strength, right? Then ultimate tensile strength. Then you look at the ductility in terms of the elongation, right? These parameters. Of course, you can also look at the toughness, which is K1C value, you can do that, right? So, you look at the yield strength of the material, ultimate tensile strength of the material, look at the elongation that happens at all, and then you can look at the K1C value, which is called as the toughness. So, the parameters, the mechanical parameters okay, of interest to design a structure. One could be yield strength, two ultimate tensile strength, three the elongation, to failure, right, failure, four the fracture toughness. If you design a structure wherein the load does not cross the yield strength of a material, right. Suppose I use a steel and carbon steel was what, maybe a 200 megapascal, 250 megapascal is the carbon steel strength, right, yield strength, and ultimate tensile strength may be about 400 megapascal, something like that, and the elongation may be around about 18%, it's a range of things that we have. So, suppose I design a structure such that the load does not lead to a stress level beyond the yield strength of the steel, what happens? It will endure forever, because it is within the elastic limit, it does not undergo any plastic deformation, right, it is within the elastic limit. So, it is supposed to endure or wrong. Suppose you have an environment coming in contact with this, structures can fail well below yield strength. It can happen even at about 25%, 30% of yield strength. Not all cases, I am saying there are cases where the metal can fail at about 25%, 20% of the yield strength. Now, cracks can grow well below K1C, fracture toughness is K1C, right, elongation is given as epsilon, sigma UTS and sigma yield strength. That is because the elongation loss can be 60 to 70%. I can lose my elongation 60 to 70%. So what does it mean? If I lose that elongation, that is what is going to be elongation means what? Ductility, right? The ability of the metal to manage any distortion in the structures that could happen during the load bearing things, isn't it? It could happen, right? So if there are going to be a distortion and if the metal is not plastically deforming, then what happens? Like a glass, you can just simply crack. So you can lead to a brittle. That only talks about safety, right? The safety here is depend upon how ductile, how tough they are actually. So if it is going to be brittle, then safety becomes a casualty. So stress corrosion cracking is a problem, and for the structures where you expect it could suffer, okay, it could suffer through that particular failures. Look at what is stress corrosion cracking. It is conjoint action of tensile stress and corrosive environment. Acting on metals, can also happen in materials also. It can happen even in glasses, it could happen in polymers, but most of the engineering materials we deal with, and especially this course we discuss more on metals, okay. But it is just not confined only to metals and alloys. Materials can happen, ceramics can fail, glasses can fail, polymers also can undergo stress corrosion cracking because the environment can interact with them. So you have three players here. One is material, other is the environment, is the stresses. When I mean stresses, I mean here the tensile stresses, okay. It is not a fatigue, it is not a fatigue stress, not a shear, or I mean we are not talking about torsion and we are not talking about compression, all these kind of things. And all this lead to SCC. So it is a synergy taking place. Please look at it as a synergy, right? It's not a cumulative. That corrosion means this much loss in weight. In air, the metal undergo this much of tensile strength. It's not additive. It's a synergy, and also not much loss in weight. Due to corrosion. Now this is a Venn diagram, we call it a Venn diagram. Now you look at this, there are three players here, the material, the environment, I mean the chemical environment here. I suppose we define the beginning of the course itself, we are not talking about physical environment, we always talk about the chemical environment when it comes to corrosion, and we talk about the tensile stresses. So in order to understand stress corrosion cracking, we need to look at the material aspect, the environment aspect here, and we need to also address the stresses. So all three we need to be understanding in order to get a picture about stress corrosion cracking, and then to say how we can control the stress corrosion cracking. Stress corrosion cracking can be taught maybe some 10, 12, 15 lectures more actually. So we will be very brief, and at best we will take about 3 classes and try to see how we can understand stress corrosion cracking of metals and alloys. Now let us go into the first aspect of the cracking. The types of cracking. Whatever be the cracking, whatever be the types of cracking, the cracking is always brittle in nature. The brittle is a very qualitative term, it is very difficult to define what a brittle is, right. I do not think there can be say anything which is 100% brittle, and you cannot say anything as 100% ductile kind of things. So it is a character of the material actually. What is the character here? What is meant by brittle as opposed to ductile? What do you mean by that? Let us look at from the perspective of what happens to the metal when you deform it actually, right.
Sir, can we say that brittleness is that there will be no elongation before the crack propagation can take place?
So there will be, okay, what is meant by no elongation, right, okay, what do you mean by no elongation?
Local yielding at the surface.
Okay, there is no local yielding at the surface, okay, more, okay, all right, you are right. What is happening? That means that essentially there is no atomic mobility taking place essentially in the success. When you apply a stress, the atoms start moving, that is what you call a plastic, right, you call a plastic deformation, right. So plastic deformation we call it. When does the plastic deformation occur? When the stress applied is greater than the yield strength. That is where the dislocations move, the atoms move, the mobility of atoms are related to the mobility of the dislocations, right. So only above the yield point dislocations move, and through which the atoms move, and so there is going to be plastic deformation. The metal takes the shape that you wanted, right. In the elastic limit, there is no atomic mobility is not going to be there. If the metal fails in the elastic regime, then it becomes a brittle. Okay. Why? Because there is no, essentially atoms do not move at all. If the stress corrosion cracking in the environment facilitates the crack initiation and crack growth below the yield point, then what happens? Then the metal will behave something like a glass, because they do not really move at all. Am I right or not? So the fracture process depends upon at what stress level the metal fails. If it fails close to ultimate tensile stress, then what happens? It is going to be nice, full, ductile. If it fails in somewhere between yield point and UTS, depending upon where it fails, the extent of ductility is going to change. Okay. So it is a qualitative parameters. I do not want to discuss too much on it. Okay, but I want you to get a feel for that, right? That means if the metal can fail below yield point, you can get nice brittle cracks occurring on the metals, but not necessarily always the metal fails in that manner. Now let us look at a microscopic level, how does the crack propagate? That is a macroscopic level, right? At a microscopic level, how does the crack propagate? We all know, we deal with polycrystalline material, right? Now the crack can grow along this way. We call it as transgranular crack. In fact, the most of the mechanical failure happens in the air are all transgranular cracks, but they are transgranular ductile cracks. Okay. Here you also have transgranular, but then these are transgranular brittle fractures. The crack also can grow okay. It can grow along and what is this called? Intergranular cracks. I will go back to some slides which I have shown you before, so that you get a clarity in terms of what is meant by transgranular cracks and intragranular cracks. I hope this is the slightly at higher magnification, lower magnification, this is the higher magnification. Now I hope you were able to see the grains here. Okay. Now look at this, the crack grows straight, cuts across all the grains. Okay. So it's a transgranular crack, so is here. You see that in the scanning microscope, it is the, please look at this is not the crack interface, right? You can break open this. This is a crack plane. This is a crack plane. It's a crack plane. This is the plane through which the crack is moving now. Now look at this. This becomes totally transgranular cracking, and I hope you are able to see some grains here. Grains here. There are grains here. There are grains here. Now you can see this also. There is a grain here. So the crack cuts across the grains. So they become transgranular cracks in nature. Look at this, and it's a clear intergranular cracks. Okay. Look at the grain here, it's a grain here, crack grows along the grain boundary. Okay. Why? The grains have got sensitized. You can see this here. The grains got sensitized, the crack grows along this. So it's a surface. The surface of the specimen, see that. You open this, you break open this, you look at the crack plane, you will be able to see the nice grains which are not elongated, right? You can look at these are all grains. You see the grain facets, can see the clear grain facets, The grain facets means the grains are not deformed like a sugar, the sugar grains, you see that, right. So they are not deformed, they are you know, I mean the corrosion has occurred selectively along the grain boundary and the crack starts moving along the grain boundary. So the grain boundaries are relatively electrochemically active. I use the term electrochemically active because it can be an anodic, can happen, it can even sometimes can have cathodic, that happens in hydrogen embrittlement case. But so if the preferential dissolution takes place here, okay, and so the grains are not deformed and you see a huge amount of intergranular cracking taking place. This is one way of looking at it. There are cases where it is not necessarily 100% intergranular, 100% transgranular, it could be a mixed kind of failure can happen, right. So, so this is what really happens. In all these cases the failure is called as I hope you heard of the term called cleavage failure. What is the cleavage failure? Anybody has an idea? The lattice that I have, right, when you apply force, atoms start moving when you have dislocations. If you know dislocations, of course difficult for that to move. Now when you pull it now, okay, assume that I use a scissor, I cut this bond, cut this bond, I cut this bond, I cut this bond, I cut this bond. If I cut this bond, what happens now? This piece becomes separate, this becomes a separate, that means atoms are intact, their positions are not changed because these are weakened now. So the cleavage fracture means essentially the bond between the atoms are broken well before the atoms could displace from their positions, okay. So this is what we call in the cleavage fractures, that what happens in the grain boundaries, what happens, the atoms cleave, right. You have one grain, another grain, in between the atoms they just cleave out, can happen. That happens, but of course here in this case corrosion can lead to that happens, but you also have intergranular cracking taking place in air also, right. You talk about temper embrittlement, all these stuffs there, okay. So they are all cleavage fractures, the atoms or you know the bonds between the atoms are I can say poor cohesive strength. It can happen and it can lead to this kind of failures. So it is very important to understand the nature of cracking in a stress corrosion cracking failures, otherwise you will get misled. You may consider that as what, it could be, you know, normal tensile failures, okay. So cracking mode is one of the signatures of stress corrosion cracking. Now if you do not identify that, then you will not identify the problem, you know. Let me just spend a minute and then I think I will close this today's discussion. This one or you get a, yeah. If you find that a crack like this, both of this are done what is called as, you guys already studied sensitization, right. It is a stainless steel, they carried out ASTM A262A test was done. Okay. You do not see any sensitization here. You see the sensitization taking place here, right? Here also you have ASTM A262A test, right? But there are also sensitization taking place. So the alloy failed by brittle fracture, case 1 and the case 2, but the reason for failure are different, right? The reason for failure in this case, it is improperly solution annealed or improperly welded, whatever kind of thing. Here everything looks okay, but the alloy is not good enough for the environment, okay. So the way you diagnose the problem is different. In this case you say it is not, the metallurgy is not adequate for the severity of the environment, okay. You need to change the alloy. Here the primary cause seems to be sensitization, right. The sensitization is related to carbon content, welding, improper solution and treatment, so many factors are going to be there. So you need to understand how the cracking takes place before we can come to a conclusion what is the root cause of the problem in stress corrosion cracking. Okay. So, so we have seen now the crack morphologies, the crack, the natural cracking, and we will end our discussion today.